Hello everyone. An interstellar object designated 3I divided by Atlas, C divided by 2025, N1, or simply 3I, was discovered by the Atlas telescope in Chile in July 2025. This marks the third confirmed interstellar object to pass through our solar system, following Oumuamua, 2017, and 2I divided by Borisov, 2019. With a hyperbolic excess velocity of 57.9763 plus or minus 0.0044 kilometers per second. Kinematic analysis prior to its entry into the solar system suggests that 3I most likely originated from the thick disk of the Milky Way, a stellar population linked to the era of cosmic noon, the period of intense star formation, roughly 913 billion years ago. If confirmed, 3I would offer a unique opportunity to study early star and planet formation processes, as well as potential biological implications in galactic history. However, a major challenge arises from the fact that 3I's perihelion will occur on the far side of the Sun from Earth, with an elongation angle of only 12.8 degrees. This makes ground-based or near-Earth space telescope observations extremely difficult, if not impossible. With an orbital inclination of nearly 175 degrees and a trajectory passing inside Mars's orbit, real observational opportunities will fall to interplanetary probes already in flight. Among the 15 spacecraft capable of potential observation, the most notable are Psyche, during its close approach on the 4th of September 2025, Lucy, in late October 2025, JUICE, in early November 2025. Other missions, such as Europa Clipper, Hera, or even solar observatories like SOHO, Solar Orbiter, and Parker Solar Probe, may also be able to capture valuable data as they pass through 3I's region of influence. If these opportunities are seized, spacecraft could conduct detailed spectroscopic and imaging observations, enabling analysis of dust and gas composition, phase angle variations, and more ultimately testing the hypothesis that 3I is indeed an ancient relic from the Milky Way's thick disk. The discovery of interstellar objects, ISOs, passing through the solar system on hyperbolic trajectories has opened an entirely new window, the opportunity to directly observe material originating from distant stellar systems. Such observations can be conducted with ground-based telescopes, near-Earth space observatories, or even through dedicated flyby and probe missions. D.E. Trilling et al. 2018, P. Guzik et al. 2019. This potential has already been examined in numerous prior studies. A. M. Heineal 2018, 2020, D. Seligman, G. Laughlin, 2018, K. Moore et al. 2021, T. Monsieur Bank et al. 2020. The first interstellar object, 1I, Oumuamua, was discovered on the 19th of October 2017. However, it could only be observed for a short period, mainly around perihelion. After moving away from the Sun in early 2018, 1I quickly faded, leaving behind only limited data. Observations suggested that it may have been a small asteroid, only a few hundred meters across, lacking a visible dust tail, yet exhibiting non-gravitational acceleration, a clue that it may once have been a comet or contained volatile material. M. Micheli et al. 2018. The second object, 2I divided by Borisov, was discovered by astronomer Gennady Borisov on the 30th of August 2019. Unlike Oumuamua, 2I displayed all the hallmarks of a comet, with a clearly visible dust and gas tail. This offered a golden opportunity to directly analyze the composition of an interstellar comet. Results revealed that 2I had a markedly different chemical makeup compared to solar system comets. For example, it was poor in carbon but relatively rich in nitrogen, along with unusual activity variations. In March 2020, as it approached the Sun, 2I fragmented, shedding a large piece, demonstrating its significantly lower structural stability compared to familiar comets. The third object, 3I divided by Atlas, C divided by 2025 N1, was discovered at a distance of 4.52 AU from the Sun, within Jupiter's orbit, and was quickly identified as both an interstellar object and comet-like in nature. Preliminary observations revealed a dust tail approximately 25,000 kilometers wide. Data obtained when it was at 4.85 AU, the 21st of June 2025, confirmed infrared emission signatures, although no clear gas emission has yet been detected. Early analyses indicate that 3I has a nucleus only a few kilometers in size, rotates slowly, and shows no strong signs of fragmentation. The goal of this study is to outline how future observations may be used to investigate 3I in order to extract scientifically valuable conclusions. Such data would not only clarify the intrinsic nature of 3I, but also help determine whether it is indeed a relic fragment from the Milky Way's thick disk, thereby shedding light on the processes of planet formation and the evolutionary history of our galaxy. The second interstellar object, 2I divided by Borisov, was discovered by amateur astronomer Gennady Borisov on the 30th of August 2019 at a distance of approximately 3 astronomical units AU from the Sun, and with an elongation angle of only about 37.2 degrees. Throughout its passage through the solar system, 2I exhibited the clear characteristics of a small comet, strong activity, with an estimated nucleus size of about 1 kilometer. Jewett and Liu, 2019. This provided scientists with a valuable opportunity to directly analyze its composition, revealing that 2I was carbon-poor but nitrogen-rich compared to solar system comets S.E. Diem et al. Liaotianling Arsha Wu. Notably, in March 2020, as it approached the Sun, 2I fragmented, shedding a relatively large piece, demonstrating that it was less stable and more prone to disruption than many native comets B. T. Bolin et al. 2020. By contrast, 3I divided by Atlas was identified at a distance of 4.52 AU from the Sun, just inside Jupiter's orbit. B. T. Bolin et al. 2025. It was immediately recognized as both an interstellar object and an active comet, with a massive dust tail extending up to 25,000 kilometers. R. de la Fuente Marcos et al. 2025. Archival data from the 21st of June 2025, when 3I was still at 4.85 AU, revealed that cometary activity had already begun. Some studies have reported evidence of infrared emission characteristic of water ice, see Opitom et al. 2025, although no unambiguous gas emission has yet been detected. A. Alvarez Candel et al. 2025. Later, in August 2025, 3I crossed the 3 AU mark, the same region previously traversed by 2I divided by Borisov, allowing for a direct comparison between the two objects. The size of 3I's nucleus remains only loosely constrained. Observations from the Hubble Space Telescope suggest a radius in the range 0.16 kilometers is less than or equal to R is less than or equal to 2.8 kilometers, with an absolute magnitude H is approximately equal to 15.423, 1 Jewett et al. 2025. Assuming a red geometric albedo of 0.04, this corresponds to a relatively dark surface, consistent with an ancient comet. Ground-based data indicate a rotational period of about 16.79 plus or minus 0.23 hours. R. de la Fuente Marcos et al. 2025, with no evidence of rotational breakup. The primary aim of this study is to encourage the scientific community to take full advantage of the unique opportunity presented by 3I, direct observation to investigate its nature, thereby deepening our understanding of the origin and characteristics of interstellar objects. Of course, exploiting this opportunity will ultimately depend on the capabilities of available spacecraft and the readiness of observational technology. In the present orbital study of 3I divided by Atlas, the authors employed the software Find Orb, incorporating 2,611 measurements out of a total of 793 observations, recorded by 177 observatories worldwide between May 22 and the 12th of August 2025. The root mean square error of this dataset is only about 0.52, 0.63 arcseconds. From these data, the hyperbolic excess velocity, v infinity, of 3I was determined to be 57.9763 plus or minus 0.0044 kilometers per second. Different datasets and calibration methods produced highly consistent results, with deviations of only a few tens of meters per second around this value. When these velocity vectors are transformed into the distant galactic reference frame, a distance of to 1,600 parsecs is sufficient. They reveal that 3I's trajectory is entirely distinct from those of the two previously known interstellar objects, 1I, Oumuamua, and 2I divided by Borisov. For convenience, the study adopts the UVW galactic coordinate system, U directed toward the galactic center, V along the direction of galactic rotation, W, perpendicular to the galactic plane. In comparison, the velocities of 1I and 2I align quite well with known stellar kinematic streams, such as the Pleiades stream and the Wolf 630 stream, whereas 3I's velocity is significantly offset, showing no correspondence with any major stream. Figure 1 illustrates the motion of these three interstellar objects in the UV plane, in the context of nearby stellar streams and galactic structures in the solar neighborhood. The results indicate that 1I is nearly coincident with the Pleiades stream. 2I is consistent with Wolf 630. 3I, by contrast, shows no clear association, and even deviates markedly from the Hyades stream. This suggests that, prior to entering the solar system, 1I and 2I may have been members of these young stellar streams. In contrast, 3I appears to have a much more complex origin, potentially emerging from an older, more chaotic galactic environment, possibly even from the ancient thick disk of the Milky Way. The Sun and the Solar System reside in the thin disk of the Milky Way. In this region, stars typically follow orbits close to the galactic plane, with vertical velocities, the W component usually less than 15 kilometers per second, K. Vieira, et al. 2022. By measuring the velocities of nearby stars, it is possible to distinguish stellar populations associated with different stellar streams, as well as the two major galactic components, the thin disk and the thick disk. In this study, the authors made use of the Gaia EDR3 catalog of nearby stars, GCNS, a nearly complete census of stars within 100 parsecs of the Sunday. This catalog includes more than 330,000 stars, covering up to 92% of stars of spectral type M9 or brighter in the local volume. As such, it provides an almost comprehensive database for investigating the kinematic structure of the Milky Way in the solar neighborhood. Gaia Collaboration, et al. 2020. However, since not all stars have measured radial velocities, only about 77,000 stars were available for full 3D velocity calculations. During the selection process, only stars with high kinematic reliability, defined as having a probability greater than 0.75 of possessing a complete 3D orbit and a normalized error below 10, were retained. From these, velocity models for both the thin and thick disks were compared with the actual data. K. Vieira et al. 2022. The values were further corrected for the local standard of rest LSR equals 233.6 kilometers per second. P. Mraz et al. 2019. The results show that the average velocity of 3I is in much closer agreement with the thick disk model. The V component of 3I's velocity, the rotational direction around the galaxy, is lower than that of the thin disk, consistent with the fact that thick disk stars rotate slightly more slowly than thin disk stars. Notably, the velocity dispersion in V for 3I is very large, a hallmark signature of the thick disk. Statistical analysis indicates that the model in which 3I belongs to the thick disk has a confidence level of 95%, implying a high probability that its kinematic origin is linked to an ancient stellar population. Independent studies AG Tupi et al. 2025, J. A. Hopkins, et al. 2025, have reached similar conclusions, suggesting that 3I is most likely the remnant of a planetesimal or comet formed over 9–10 billion years ago in the Milky Way's thick disk.